In this video, we're going to continue with protein purification and look at chromatography. And what chromatography is that you use different phases to separate your components. So your two phases are generally, you have a mobile phase, which is either liquid or gas, and you have what's called a stationary phase, which is usually some kind of solid matrix with holes in it. And the way chromatography works is that you have a column, and in this column you have your stationary phase, and you run your mobile phase over it to separate components. And we'll look at how we separate those in the next slides. In practice, how this works is that you use what's called a HPLC, or high performance liquid chromatography, where you have this fancy machine hooked up to a computer. And you use very thin columns, 3 to 300 micrometers in diameter, and you flow your or you elute your column under extremely high pressures, 5,000 psi. This allows for repeatable and fine and highly specific purification. Speed, resolution, and reproducibility, since it's all computer controlled. So that's how you do it. If you take lab here, we do not have this fancy equipment, so we'll do it using a tabletop method. Now let's look at the various types of chromatography available to us. And the first type we're going to look at is called ion exchange. So if your target protein has an overall charge, we can use ion exchange chromatography to purify your protein. And we have two different types of beads we can use. If our protein is positively charged, we can use negative beads, which are carbimethyl or CM beads. This is called cation exchange. So cations are positively charged ions. So cation exchangers have negatively charged beads. Here's what a CM bead looks like. This hydrogen would be gone, so it would be OO minus. Rather, if you have negatively charged proteins, you would use a positively charged bead. Commonly we use DEAE, which is shown here. Here's the positive charge. This is called an anion exchange. Anion is a negatively charged ion. So anion exchange, you're exchanging negative ions, right? So the way a column works, either a cation exchange or anion exchange, you put your sample mixture in the column and you use low salt. And low salt will work to remove anything that is not highly bound to your media. So anything that doesn't bind strongly will elute or come off the column, which is red in this example. Then, after that, you use a high salt buffer or a elutant. This high salt concentration buffer will outcompete the proteins that are stuck to these beads. It will basically kick the proteins off. And the stronger a protein is attaching to these beads, the slower it will move off the column. So you can separate your proteins here. So using this high salt buffer, we are outcompeting the protein with our beads, either cation or anion exchange, and the proteins are coming off. Now, in this example, these proteins are colored. In reality, though, proteins are usually not colored, and so we can use 280 nanometers light absorption, as we talked about in the previous video, to measure when proteins come off. So if light is being absorbed at 280 in these drops, that means it contains a protein. Another type of chromatography we can use is called hydrophobic interaction chromatography. Here, we are purifying proteins through hydrophobic interaction. So here our beads have octyl, which is 8 carbons, or phenyl, which is the carbons in rings. These are hydrophobic groups, and so they bind to hydrophobic regions of proteins. And so the way this works is that under high salt conditions, hydrophobic interactions are extremely strong. So the way to read this is the red is your bead, orange is hydrophobic regions, blue is hydrophilic. So if your protein has any hydrophobic region under high salt conditions, it will bind to your beads. Under low salt conditions, hydrophobic interactions are not strong. So these weak binders with not a lot of hydrophobic regions will come off the column first, and things with a lot of hydrophobic regions will come off the column last, or elute. Elute basically means come off column. So by, again, having different salt concentrations, by exploiting hydrophobic interactions, you can elute proteins off columns or separate proteins. Another way we can use chromatography is through what's called gel filtration or size exclusion or molecular sieve. All of these separate proteins by size. Here, our stationary phase are beads, but these beads are filled with holes or pores. And the way this works is that if your protein is small, it will go through these pores and it'll take longer to elute. While if your protein is big, which are the blue proteins, they cannot enter these pores. Therefore, they will go through the column faster. And the way these pores work is that the pores are different sizes. So you can actually separate proteins on size nicely. Usually in gel filtration, when you work with a bead, there will be a cutoff size. That is, proteins bigger than this size cannot go into the bead at all, while everything smaller than that can be separated linearly. That is, there's a linear relationship between the volume of solvent you need to elute and the size of your protein. Because the smaller it is, the more time it will take to come out of the column, because the more time it spends going through these pores. And that's called gel filtration, or it's also called size exclusion. Now, another type of a chromatography is called affinity chromatography, and this is used a lot with proteins, because proteins can actually bind, a lot of proteins can bind to specific molecules, or these molecules that are being bound by proteins are called ligands or ligands. Depending on who you're talking to, they will pronounce it differently. The majority of people say ligand, I say ligand. And exploiting this binding of proteins to ligands is called affinity chromatography. And these are all non-covalent interactions, which means there's no covalent bond being formed. So you have beads that have your ligand on it, and anything that doesn't bind to this washes straight through. So for example, here we have 3 different types of proteins. Red binds to our bead, which is to our ligands, which is black. Green and blue don't, so they go right through the column. Then, to get off your protein, you change your buffer to outcompete your protein again. And you kick your protein off. So affinity chromatography, if your protein binds too tight and doesn't come off the column, then you can't use this technique. Most proteins don't bind that tight though. There's a special type of chromatography called immunoaffinity chromatography, where your ligand is an antibody. So we already talked about ELISA. So it's similar to that, but now in a column, and you don't have a secondary antibody because eventually you want to kick off your protein. One common way we use affinity chromatography is by using our metal beads. So usually zinc or nickel. That's what's in your beads. It's zinc or nickel. Then we modify our protein through site-directed mutagenesis, so if you remember that from previous slides, to add a histidine tag. That is, we add about 6 histidines in a row, either on the N-terminus or C-terminus of our protein. And these histidines will bind to zinc or nickel. And so anything that doesn't have 6 histidines in a row, which won't appear in nature, will walk through our column, and our protein of interest will stay on the column. Then, to get our protein of interest off the column, we add salt. Salt will outcompete for these nickel and zinc beads, and our protein will come off. Now, those were columns. Let's look at gels, and we're going to look at polyacrylamide gel electrophoresis, or PAGE. Now, PAGE separates proteins by charge and by size. The pH of a gel is roughly 9, so almost all proteins that are going through a gel will be negatively charged. And the way a gel works is that on the bottom, it's positively charged. At the top, it's negatively charged. You run, that's because you put an electrode there. You basically hook it up to an external power source, bottom positive, top negative. Most gels are negative, and so they run through. Now, the gel itself is a porous mixture. It's a porous solid mixture, more or less. And so big proteins get caught up in the pores. They hit the gel. Small proteins are able to go through this gel much faster. And so that's how you're separating proteins by size. Most people, however, use SDS-PAGE. SDS is you add sodium dodecyl sulfate, shown here. SDS is detergent. And so when you add SDS, it's a detergent that's negatively charged, so you're making sure that all proteins are negatively charged. And SDS also binds non-specifically, which means that based on your size, you have more negative charge. That's how we're separating by size. The problem with this, though, is that SDS will unfold your protein. So SDS-PAGE is only used to determine if your protein is there. Once you go through SDS-PAGE, you can't use your protein for experiment. So what happens realistically is that you take a small sample of your protein. After you purify it, run it through SDS-PAGE, and this is what it looks like to see if your protein of interest is there, and also to see what size it is, how big is it. And for this, if you remember, proteins can have multiple subunits, and these subunits can be connected through disulfide bonds. If 2 cysteines come together, they'll form a disulfide bond. This can interact, or this can give false size readings. So in addition to SDS, you usually add something to break disulfide bonds, and that would be 2-mercaptan ethanol. And then you can make a plot that looks like this. That is, how far did my protein go through the gel versus its size. And that's usually a log plot. That's why the scales look so weird. And finally, we get to a special type of electrophoresis called 2D gel electrophoresis. So we've talked about proteins for a bit now, and amino acids. So proteins usually have a charge to them. And we also talked about pI before. pI is when a protein, at that pH when a protein is neutral. So if we're in an electric field, which we are, that's electrolysis focusing. So we have a gel that has different pHs as we move from left to right in the gel. And we have proteins on this gel. So we load our proteins here. Then we run an electrocurrent through these proteins. And whatever the pI is, once our protein enters that region of pH where the pH equals its pI, this protein is now neutral charge. And a molecule that is uncharged or neutral will not move in an electric field until it will stop on the gel. Then we do SDS-PAGE, right? So these molecules are covered in SDS. Then they can move down the gel, and so we're separating not only by size, but by charge as well. This is very useful in proteomics. So let's say we have a protein, or sorry, we have a cell, and we just want to know what proteins are in this cell. So we can break open the cell, and all the proteins we can use 2D gel electrophoresis. Then we can cut out a spot and determine what that protein is through mass spectrometry, which we'll talk about later. The last technique we're going to look at today in this video is ultracentrifugation. Ultracentrifugation separates proteins by mass, and this is actually how you also make atomic bombs. We're not going to go into that though. Ultracentrifugation, which is shown here, you spin your samples at 100,000 revolutions per minute, or basically your molecules are experiencing 1 million times normal gravity. Now, how this works is that you take your sample, and below your sample is some kind of gradient. Usually it's sucrose, where you have high sucrose density at the bottom, low sucrose density at the top. And it has to be inert, that is, it doesn't interact with your proteins. And when you spin your sample at these such high rates, they will separate based on size and shape as well. So things that are lighter will go towards the top here in the blue, and the things that are heavier will go towards the bottom. And where they end up in this gradient, we can measure them. We give them units of Sedbergs, or S. These S units are used in ultracentrifugation, but they are not additive. If you know the ribosome is made out of two parts, a 30S and a 50S. But combined, a ribosome is a 70S. That's because it all has to do with not only mass but shape. And this is really useful if you have proteins made out of, or big protein complexes made out of different proteins. You can separate these proteins by ultracentrifugation. And that is finally it for this video, and I will see you in the next video.